So I'm Roger Edwards, Storm Prediction Center, lead forecaster there. I've been at SPC since April of 1993. Was at the Hurricane Center before that. Severe Storms Lab here in Norman before that as an undergraduate and part of my time in graduate school here at OU. And so made the full circuit back here, and my background at NSSL and NHC and SPC has imbued me with a deep passion for a specialty of tropical cyclone tornadoes, and so I hope to give you a little bit of a flavor for that today. So my hometown is Dallas, and so it was very ironic that Tropical Cyclone Hermine, the remnants, produced tornadoes in Dallas back in 2010, some of which actually fairly strongly resembled famous tornado on April 2nd of 1957 that was a killer tornado in Dallas. And that was this one here. This one that's at the lower left was a multiple vortex in southeast Dallas County near Seagoville. Several separate tropical cyclone supercells moved through the metroplex and produced tornadoes that were destructive, but fortunately small, didn't kill anybody. This one evokes eerie memories of the '57 tornado because the view is similar. Looking from downtown, you can see the Los Anatole Hotel at lower right out toward some of the same area. In fact, the paths crossed and the tornadoes look pretty similar to the one in '57. But it's not just an American thing. I mean, the physics of the atmosphere does not change worldwide, just the frequency of the juxtaposition of the ingredients. And so a few years back we had killer tropical cyclone tornadoes in China. In fact, from the news article at the left, you can see one of them that has just a fantastic spray of debris around the vortex, eerily reminiscent of Chuck Doswell and Al Mohler's video from June 8th of '95 in Pampa, Texas. And but it was happening in China, in southern China. Upper right, you can see the power is out in the city. That's sort of an indirect impact of these events. Absolute gridlock. And this is a really neat view looking down on the bottom of the tornado moving across a rice paddy in southern China as well. Deadly event though, 3 people killed in 2 separate tornadoes. So I'll run through some facts here for a quick overview. They're most common in the area of the storm where the winds are actually less than 50 knots. Tropical storm force are weaker. Just because the wind is stronger doesn't mean the shear is stronger. In fact, weaker surface winds may contribute to stronger vertical shear in a vector sense. And that actually is important when you're dealing with weakening tropical cyclones moving inland. As I'll show, they're most common in that north-northwest to southeast sector. They're most common in damaging from many supercells. They tend to be weak, EF0 to EF1. Some EF3s, I'll show a bar chart later. We had 2 F4s since 1950. One of them at after midnight that moved on shore in Hurricane Carla and did F4 damage in Galveston. Occasionally, they are reported from non-supercell radar features, and on the SPC publications page you can go to a paper that I did with Andy Dean and Rich and Brian Smith on non-supercell TC tornadoes if you're interested in those. And there's a sharp decrease about 500 kilometers from the coast, and I'll show a map that illustrates that. They're more common during the day. Again, these subtle features that I talked about, subtle areas of heating, can make all the difference in the world between having CAPE in a profile and not having CAPE in a profile. And that does matter in deep saturated environments or nearly saturated. Again, they can occur over water and move ashore. That's happened a lot of times. They occur in every stage of classification. I'll show a pie chart with the distribution of that. Most of them occur from classified depressions and storms, not hurricanes, interestingly enough. So here's what I was talking about being within 500 kilometers of the coast. This is part of the TC Tour Climatology. It's a database I maintain at SPC of tropical cyclone tornadoes since 1995, the WSR 88D era. I started it at 1995 because That way, we would have an apples-to-apples basis for comparison through a climatology of TC tornadoes. Before 1995, different verification practices, no network of 88Ds to detect, and so the ratio of tornadoes of different ratings was a lot different as well. But the practice of gathering the data has been relatively constant since 1995. So that's the start of the data set. It goes through 2015. I don't have all the 2016 data finalized yet because we don't have our final tornado data finalized at SPC yet. That'll be added shortly. F2, F3, EF2, EF3 are in blue. The weak tornadoes are red dots, and so you can see even from this chart in that period, 16-year period, that we're overwhelmingly dominated by weak tornadoes, but not completely. By category, major hurricane is in purple. Category 3 or higher. Hurricanes Cat 1, Cat 2 are in red. TS is in yellow. TD is in green. And post-tropical lows, unclassified systems that still have tropical characteristics, count those two. Those are in that gray color at upper left. And so you can see that the TC tornado climatology is overwhelmingly dominated by non-hurricanes. Part of the reason for that is just there's so many more storm hours of sub-hurricane classifications inland, over land, than there are for the hurricanes. It really has not as much to do with physics as it does with temporal factors and storm decay. By year, again, I'll add 2016 shortly, but there won't be many of them. Our sample size has been really, really low the last several years. But you can see the distribution varies widely. Those huge years of 04 and 05 were also tremendous years for tropical cyclone landfalls, major hurricanes in the United States. At the time, we thought, what is happening? Cataclysm, world coming to an end. You know, has global warming slammed us with hurricanes all of a sudden? Who knows? Well, no. The answer to all those is no. We just happen to have two of the most active years on record for both hurricane landfalls and TC tornadoes back to back. And back to much the same trend ever since. Highly variable, from 0 tornadoes and TCs in 2009 to over 300 in 2004. We average about 60 to 70, depending on how far back you want to go in the data. I was talking about the climatology with respect to before and after the 88D. So that's what these two charts represent. The one on the left is the record of TC tornado F scales in the pre-WSR 88D era, 1950 to 1994. And this is from a climatology done by Laurie Schultz and Dan Cecil back in 2009. So the data only goes up to 2007 from their climatology. But you can see, comparing the pre-88D era to the 88D era on the right, again, F-scale ratings, tremendous increase in weak tornadoes. Now, did the radar somehow, does that 10 to 11.1 centimeter beam somehow magically zap the atmosphere and cause a lot more weak tornadoes to happen since we've deployed the 88D? I don't think so. It is totally an artifact of sampling and of intensive and rigorous storm warning verification efforts by the National Weather Service. This is why you shouldn't trust blindly any data set you ever analyze, because this is a complete artifact of human data gathering practices. And so this applies no matter what you're researching or what you're looking into for the rest of your career. A vivid example of how artifacts and secularities in the data can influence the data. This on the right is probably much more representative of the true climatology because we are trying to verify warnings and we are trying to verify occurrences so much more rigorously than we used to. So that's one of my side rants among many. So if we look at the TC tornado record before and since, also in terms of absolute numbers instead of F-scale, 45 years we had 700, a little over 700 events. And in 13 years, after the deployment of the radars, we had almost 1,000. Again, I don't think that radar beam suddenly caused a ton of TC tornadoes to happen. It's all an artifact of data gathering. That's why I started the TC tornado data set at 1995, so that we would have a relatively even apples to apples comparison. So Rich, Brian, Andy, and I looked at tornadoes throughout the year. In this case, it's right-moving supercells, which produce the overwhelming majority of TC tornadoes as well. From a TC and non-TC perspective throughout the year, so you can see January through December. The TCs are in colors here, and they're not the right colors, of course, as Ben noted would probably happen. But discrete cluster and line embedded supercells are the convective modes. Of those, if you add those three together, you can see that supercell TC tornadoes dominate the United States tornado climatology in the month of September, when TCs reach their climatological maximum, and are very important in August and even back toward July, and to a much lesser extent October. So they are important climatologically, and they can be important impacts-wise. They're often overlooked impacts-wise because they occur on the periphery of the TC, and I'll get to that shortly. You want a winner in the TC tornado sweepstakes? Ivan, 2004. As far as we know, it set the all-time record for TC tornado production, 118 in 3 days. That third day up in Maryland, DC, West Virginia, and Virginia, that was, to this day, as far as I know, the only moderate risk we've ever issued for a TC tornado situation, and that verified. Very dense coverage of tornadoes in Northern Virginia and the DC area. A 3-day cycle. This 3-day cycle is strongly tied to diurnal processes. You can see the 18Z positions plotted each day, and each day they tend to occur northeast through east of the midday to early afternoon TC center position, really concentrated tightly. So here they are with respect to the position of the center of the circulation of Ivan at the time the tornado occurred. Okay? You can see they're extremely concentrated. This is all 3 days put together, 118 events, very tight concentration, tighter than usual actually, between about 200 and 600 kilometers from center and in a sector from about 10 degrees on around to about 110 or 120 degrees. Most of them don't tend to concentrate that tightly. That one did. People like top 10 lists. I'm not going to spend a lot of time on this, but this is the top 10 that we know of all time. Beulah in 1967, there was a formal paper published on that documented 115. There may have been more. We don't know, but the documentation of the ones that could be found was very, very good. Notice how many of those are 2004 and 2005 events that you saw on that pie chart. One of these is a tropical storm, Faye, from 2008, which was another spike on that chart that I showed you. By EF rating, here's how they're distributed. Overwhelmingly weak, EF0, EF1, a few EF2s, 3 EF3s from 1995 to 2015 in the TC TOR data set. The 2 EF2s on record were from storms long before the data set starts. Again, sampling is everything. Now, I've got well over 1,000 TC tornadoes in this data set, but it doesn't grab those 2 Grisoulis rated F4s. They are diurnally related, as I noted before. So we'll go into some more of these climatological aspects that are relevant for forecasting. Here you have moist adiabatic lapse rate environment. Again, like I said before we got the presentation started, so even subtle warming on a sounding profile can give you enough instability that you need. The drying aloft, we don't think that's directly a physically related thing as much as it permits slots of heating and differential heating that can set up transient, ephemeral, temporary baroclinic zones inside the TC envelope. Those, in turn, can act as boundaries of opportunity for supercells to interact with and generate vorticity for supercells to use in that environment. So you can see the decrease at night in numbers using a 3-hourly bin and by Z time, but in the nighttime period, that's how it corresponds to Z time in the central and eastern U.S. for the most part. So I bend them by 3-hourly bins, and you can see the diurnal increase once you get to be during the morning through midday and then through early and late afternoon. The bars on the bottom represent the significant tornadoes. Again, not many, but those also tend to increase at night or during the day as well. It is really like night and day. At nighttime, TC tornadoes are less common. They do tend to be concentrated closer to the center of the storm at night because they're less tied to that diurnal variation in CAPE that tends to happen more on the periphery where you get better heating. There's a tendency toward more non-supercell tornadoes inward toward the center, and there's fewer supercells overall at night, which you would expect. Weak convective inhibition, weak CAPE. During the day, again, more common overall, more CAPE in an environment that has strong shear regardless. Here is a graph with two different presentations on a polar plot of the ASRANs of TC TOR events from the center of the storm. I'm going to go on another quick side rant. I don't believe that anything in here is legit. If you go to that 2012 paper, you will get to read a more protracted, formally reviewed rant from me on eye-wall tornadoes. I am unconvinced that eye-wall tornadoes exist. And for reasons why I'm unconvinced, go to that paper. I've never seen a picture of one, never seen video of one, haven't seen evidence from mobile Doppler radars deployed in eye-wall situations that there is continuity of a swirly at the ground level into the convective plume of an eye wall. Hasn't happened yet. So I treat it like I used to live in the state of Missouri, which I did. Show me. Hasn't happened yet. So I'm not convinced that those reports are real, but they're in the data set regardless because they're reports. Anyway, even if you throw those out, TC tornadoes tend to happen in a Cartesian north, south, east, west sense, which is on the left from roughly north through south, southeast of center, with the greatest concentration in the northeast quadrant. The distribution is a little bit more scattered once you look at a motion relative framework. The reason they resemble each other so closely is because in the mid-latitudes, most tropical cyclones tend to translate with a strong component towards north anyway. However, those that tend to buck westward or southwestward, physically they're not that different in terms of where the shear distribution is, but like Hurricane Beulah in '67, which moves southwestward into the Texas coast, those tropical cyclone tornadoes, and they're not even plotted on here, tend to be thrown into the left rear sector. So I advocate using a Cartesian framework, which is much better aligned with mid-latitude shear profiles in the horizontal and in the vertical than motion relative or right front. Use northeast, not right front when you're referring to climatology. The difference field between the two essentially is at lower left, because what I did was I took the motion relative ASRAN of all tropical cyclones with a southward motion component. In other words, those that anomalously went back toward the west, southwest, southwest, or south, or even southeast. Not very many, not a big sample size, but you can see they're distributed differently in a motion relative framework. That difference field is why I advocate going Cartesian and not motion relative for the climatologies. Tornadoes are more common in the southeastern sectors as tropical cyclones weaken. This shows that. The top left is all TCs, the top right is hurricanes, the lower left is tropical storms, and the lower right is tropical depressions, unclassified, remnant lows. So, does anyone want to venture a guess as to why tornadoes are more common in the record in the southeast sectors as tropical cyclones weaken? Please, somebody guess. I won't embarrass you. Okay, that's actually a good physically based guess. Any others? Now, the fact I'm asking this question probably psychologically tells you that the answer is probably way out in left field, and you're going to be right. Well, the reason for that is that the sector of hurricanes and intense tropical cyclones that are producing tornadoes is usually over water, the southeast sector. Once the whole TC moves inland, it tends to weaken to below hurricane strength, and we start to sample the tornadoes that are occurring in the southeast sector of the storm better. It has nothing to do with the physics of the storm and everything to do with sampling. Again, know your data. Know your data. So we'll switch to some TC tornado forecast concepts, ingredients-based thinking. Again, just like in mid-latitudes, the problem is not that different, just the distribution of the ingredients. Moisture, instability, lift, and shear. Again, the moisture is not much of a problem. The instability is. That is the hard part. It's forecasting the instability. Sources for lift, subtle boundaries, subtle baroclinic gradients, synoptic front interactions, differential heating zones, confluence lines. In other words, spiral bands in that scenario. Interactions between spiral bands and baroclinic zones are notorious TC tornado producers because you have maximizations of convergence, vorticity, and at least on one side or another of that boundary, favorable buoyancy. Maybe both. I'll show more about that later. And the peak photographs, for reasons I already elucidated, tend to occur in the climatologically favored sector that you saw. Otherwise, we wouldn't have tornadoes concentrated there. But frequent hand analysis is crucial still, because we can slow down, swim in the data, examine the scenario, take the time to really dive into the subtleties of the event. And it's fun too. I mean, we get to play with crayons, but we get to do it with a noble purpose in mind. And that is to diagnose subtle environments and environmental changes from hour to hour, from 2 hours to 2 hours, that are subgrid scale for most models. Most American models do not handle tropical cyclone gradients in kinematics well. Kinematic gradients are awfully handled by most models. They don't depict these things well. They're not sampled well because they're mesoscale systems, in part. And we don't have observation stations. We don't have Oklahoma mesonet stations every county or two throughout the Gulf Coast and the Atlantic coast. Hopefully that'll eventually change. But even then, the resolution of these features is sometimes a few kilometers. It helps to analyze, it really does. But objectively analyzed parameters can be useful if you understand the limitations. Know your limits. I did test 2003 to 2011 TC tornado environments for our surface OA parameters, like you see online. What I found was that there was little difference with any parameter between weak and strong TC tornadoes. Again, because they tend to occur in close proximity to each other with subtle differences in environments. You might get a bunch of EF0 or EF1 rated events with a couple of EF2s sprinkled in there, and there's really not much environmental distinction between the two at the scales we can detect. That's the key. There obviously is a difference, or you wouldn't have different strength and longevity of tornadoes. We just don't detect it. High precipitable water, weak lapse rates, low mixed cape versus mid-latitude tornadoes, but a lot more shear. And what that does is it results in a lower and more compressed distribution, if you look at box and whisker diagrams, of supercell composite and STP for tropical tornadoes than those for mid-latitudes. Know and understand the ingredients that go into these bulk indices. Don't just blindly use them out of expediency because you're running short on time. You got to know coming into the forecast game what you're dealing with. The surface OA fields were based on the RUC, the Rapid Update Cycle, which is a long gone model, kicked to the curb a few years back in favor of the Rapid Refresh. But the RUC was highly unreliable and inaccurate on wind and pressure fields and hurricanes. It wasn't designed for that purpose. It wasn't the HWRF. And There were too few cases on the rapid refresh. You saw the TC tornado distributions in recent years. There just haven't been that many cases to analyze versus the rapid refresh to say how much better or worse it may be. So our surface OA fields for TC situations may be generally useful, may help you kind of look for sneak attack areas if you see some capes suddenly show up in them that you didn't expect. But in a sense of specifics, I would not use them very closely or very intensively. Indices and parameters, remember, they're diagnostic, they're not prognostic. They tell you what went on last hour. They tell you what might go on this hour if you extrapolate and infer, but they can change a lot from hour to hour. And with these subtleties and cape dependence, they really can. You have to understand the ingredients, the model biases that go into the indices, and they are still largely untested for TC environments in the models we currently use. The lesson from all this is that there's no substitute for physically understanding the environment you're dealing with. Don't take shortcuts in forecasting. Analyze the situation, examine it, look at it closely in detail. And there's still no substitute in these subtle situations for hand analysis. Sounding analysis. Remember that Chinese event that I showed you earlier? This was a sounding along the Chinese coast in the northeast sector of the tropical cyclone, of the typhoon, about 7 hours before the tornado event started. But the environment didn't change that much except for some diurnal destabilization. So I consider this about as representative of a sounding as you're going to get, especially over there. So you can see the hodograph is turned around, and well, the red's not showing up that well, unfortunately. It will on the presentation, on the copy that hopefully Ariel will post. That's really unfortunate that that hodograph is not visible, that the reds are gone, because that's the low-level hodograph. But they are large hodograph, displaced to the left, with a supercell moving toward the northwest in a high SRH environment. And just enough cape, you can see how the lapse rate, you can infer at least, since the red curve is not on there very well, how you have a deep saturated profile, nearly saturated profile, with just a little bit of heating and mixing at the bottom that bumps the lifted parcel to the right and gives you cape that you would not normally otherwise have. There's a difference between your day and night distributions, and the reason for that. What did it do? Well, that's what it did. That is a phenomenal looking tornado there in China with a horizontal accessory vortex around it. I would cut off body parts to see more of that in real life. I've only seen it a couple of times, one of them on May 24th of 2011 with the Piedmont tornado, and that was an F5. That is an intense tornado with a lot of vorticity. It's just a matter of what kind of damage is it doing. But that's what they can do. Again, analysis is very crucial. Al Patrica and I in 2006 analyzed TC events with regard to surface data, and so we found 4 types of cases. Shear limiting, in other words, the shear is favorable on one side of the boundary, but not the other, and the buoyancy is favorable on both sides. So you see the tornadoes are concentrated to the side of the boundary, in this case a warm front, where the shear was the best. Buoyancy limiting, the shear is favorable on both sides of the boundary, but it was cold and stable on the west side. In this Carolina coastal boundary, Florida interacted with a cold air damming front, so the tornadoes were all in the zone where the shear was at least adequate and the cape was there. And as soon as those supercells hit that front, they stopped producing tornadoes because they went into cold air. Shear buoyancy overlap, Charlie. Hurricane Charlie did something like this with a warm front that extended northeast of the storm. The graph on the left tracks the warm front every few hours in time, every 3 hours. And then on the right is the track of the TC itself across Florida. And so you can see the tornadoes are almost entirely concentrated in the warm frontal zone, in the Bear Clinic zone, where you have buoyancy on the southeast side, but not as much shear. Favorable shear on the northwest side, but not much buoyancy. So there's an overlap there. Again, analysis is so crucial to determining this. Sounding analysis, hand analysis of data, upper air analysis, satellite data, it all has to be integrated together. And that's before you even look at radar, if you're issuing warnings, to really understand what's going on.